Hello everyone, we are batch number 4 and our project is power factor correction using IC L6561. Basic definition of power factor. Power factor may be defined as the ratio of real power to apparent power. Real power is the capacity of doing a work in certain time and apparent power is the product of voltage and current. In many of the applications, apparent power is always greater than the real power. Let us now understand the reason for it. Most offline appliances use a bridge rectifier associated with a bulk capacitor to draw DC voltage from the AC supply. This technique results in high harmonic content which will reduce the power factor. In effect, a simple rectification technique draws power from the mains only when the instantaneous AC voltage exceeds the capacitor voltage. This occurs near line voltage P and results in high charge current spike. Consequently, a poor power factor in the range of 0.5 to 0.7 is generated. Loads are basically of two kinds. One is linear load and the other one is non-linear load. Linear load comprises of resistive load where both current and voltage waveforms are in phase, inductive load where the current waveform lags the voltage waveform, and capacitive load where the current waveform leads the voltage waveform. Next comes the non-linear load. Since the current in this system is interrupted by constant switching action, the current contains frequency components that are multiples of power system frequency. In case of non-linear loads, power factor definition changes, that is the product of displacement power factor and distortion power factor. In linear loads, we just consider the displacement power factor.
Now I would explain about boost converter operation. The key principle that drives the boost converter is the tendency of an inductor to resist changes in current. In a boost converter, we get an output voltage which is always higher than the input voltage. When the switch is turned on as shown in the figure, current flows to the inductor and energy is stored in it. When the switch is turned off as shown in the figure, the only path available to the inductor current is to the diode and capacitor. Now the stored energy in the inductor tends to collapse and its polarity reverses such that it adds to the input voltage. Thus, the voltage across the inductor and the input voltage are in series and together charge the output capacitor to a voltage higher than the input voltage. Now I am going to explain about power factor correction IC, that is IC L6561. Among many PFC techniques available, the peak current control, average current control, hysteresis control scheme, borderline control and discontinuous current PWM control scheme, we are using IC L6561 which uses borderline control scheme. This is the AC supply voltage given to the diode bridge rectifier. The output of the boost converter circuit is given to negative terminal of a voltage error amplifier via potential divider circuit. This signal is compared with a reference voltage which is predetermined. The output of this error amplifier is then multiplied with a rectified supply voltage which sets the IP reference waveform. This is the IP reference waveform. This IP reference waveform or signal is given to the negative terminal of the comparator. The current flowing through the MOSFET is given to the positive terminal of comparator. The zero crossing of inductor current is sensed by using a zero current detector. The output of this zero current detector and comparator are given to the SR flip-flop. When output of zero current detector is high and comparator is low, the SR flip-flop is set, that is MOSFET is switched on. The MOSFET is turned off when IP reference is higher than when the inductor current is higher than the IP reference. This is the turning off and current waveform is inductor current is like this.
These are the CTs and PTs which are used for the power factor measurement. These are the loads and this is the PFC circuit. This is the thyristor and This is the thermistor, this is the line filter, this is KBL10 or diode bridge rectifier, this is input capacitance, this is boost inductor, and this is the MOSFET IRF840, and this is the boost capacitance. Coming to the IC, the pin 1 describes about the output voltage as a feedback via a potential divider, and pin 3 is a measurement of a pulse rating DC via a potential divider. Pin 4 is the current sense through the MOSFET, and pin 5 is the current sense through the inductor, and 6th pin is a ground terminal, and 7th pin is a pulse which is given to the gate of the MOSFET, and 8th pin is which is given as 18 volts input through the Zener diode to the pin 8.
Coming to a software simulation, this is our AC input of 230 volts. A part of this AC input is taken using this potential divider circuit. This is our diode bridge rectifier which helps in converting our AC input 230 volts into a pulsating DC output voltage. This output voltage, pulsating output voltage, can be measured across this output load resistance of diode bridge rectifier. We can see this waveform of pulsating DC here in this scope. Now, coming to this one, this is our boost inductor. Then this is our boost capacitor. The boost capacitor along with this boost inductor is used to boost the input voltage of 230 volts to around 380 volts DC. We can also measure our voltage and current across this load resistance of our circuit. Here this is our MOSFET IRF840. This IRF840 MOSFET is switched on using this IC implementation. As in MATLAB simulation, we don't have a direct IC which is used to turn on or switch on this MOSFET. We have used a combination of certain components which works as a PFC IC so as to turn on this MOSFET. We can also see the pulses of this PFC IC here in this scope. These are our pulses which are given to MOSFET for switching on. Now we can see the input current and voltage waveforms in this scope. Here this is our output voltage and this is our current waveform, which are almost in phase with each other.
Take it out.
This is the output voltage and current as shown in the CRO waveform. They are in phase because of the presence of PCB. We can see small ripples in the current because of the presence of CT and PT in the measurement circuit. This is our load, inductive load.